Welcome everybody. I'm delighted to introduce Abid Ali, who's a Hill Assistant Professor here at Rutgers. And Abid and I have some work history. He visited Rutgers in 2011. And we did another project, which is somewhat relevant to what Abid will talk about today. That early work formed his first PhD thesis in Pakistan. He got a second PhD thesis at the University of Edmonton. And today he's going to speak about Eisenstein series on arithmetic quotients of rank 2 Kac-Moody groups over finite fields.
Okay, should I start?
Yes.
Okay, thank you so very much for the introduction. Am I audible to everyone? Or should I be loud? Okay. Okay, so before I start my presentation, I think being the last speaker of this term, it's a good time to appreciate the organizers of this seminar, Lisa Carbone, YC Wang, Jim Dubuski, and Siddhartha Sai, for providing this wonderful forum. I mean, beside these several interesting talks, I always enjoyed pre and post chit chat on this forum. All right, so in today's presentation, which is on Eisenstein series on the arithmetic quotients of rank 2 Kac-Moody group over finite field. And let me say that this is joint work with Lisa Carbone, Q-Han Lee, and Dongwen Liu. And Paul Garrett has written an appendix about the meromorphic continuation per SL2R, which I will talk about at the end of my presentation. All right, so let me start with motivation, and let me introduce finite field, which we denote by this little k, and it has q elements. And we consider a particular Chevalier group, PGL2, over the field of formal line series. So let me recall that for a ring R, PGL2 R is a quotient of general linear group by its center. This group has a maximal compact subgroup, which we denote by K, and it is PGL2 over the ring of formal power series. And we denote by gamma a discrete subgroup such as PGL2 over polynomial ring. Now, the homogeneous space of G by K, which we denote by X, has a G action on it. And the pair gamma with this homogeneous space, gamma acting on X, is similar to what we have modular group acting on upper half plane. Okay. This space X, homogeneous space X, can be endowed with a structure of tree on which gamma acts without inversion. And then we have a natural adjacency operator, which I will define more precisely in next few slides. It induces an operator which is denoted by D sub.
Abid, can I ask you a question? So
yeah,
this PGL2 actually acts on the complex plane minus the real line. It doesn't preserve the upper half plane.
No, I mean, here we have a tree. We are not talking about.
No. But what I'm just saying is that I'm just trying to understand I understand it's completely an analogy, but the PGL2 action is on both half planes, right, or not?
No. So the analogy is somewhat different. If you form G mod K for PGL2 in K and the compact subgroup, so this is actually a totally disconnected set of points. You don't get any plane at all.
Yes.
And so,
No. Okay, yeah. Okay, so I think I understand. Let me just think about the question.
Let me just finish by saying you can repair it to a symmetric space by making the set of points the vertices and edges of a building. So the building is the analog of the upper half plane.
Upper half plane, yeah.
Okay. Yes. Okay. Fine. Yeah.
So in this setting, Eisenstein series are eigenfunction for T gamma whose eigenvalues represent the continuous spectrum of T gamma. So this summary is prepared from the paper of Efrat. And negotiate. Our main motivation came from the paper of Nagoshi. So let me describe briefly what happens in case of Kac-Moody groups. So Kac-Moody groups can be viewed as infinite dimensional analog of Chevalier groups. And they may be given by set of generators and relations. And we consider Chevalier type construction by using integrable highest weight representation, which was given by Carbon and Garland back in 2003. And the main object for today's presentation is rank 2 Kac-Moody group over finite field K. This group is analog of similar to PGL2 over the field of formal Laurent series, and there is a pair. It has a pair of subgroups which we denote by P1 and P2, which play the role of K in Kac-Moody setting. And the Brouillard-Titz building associated with the Kac-Moody group is a tree, homogeneous tree, which I will talk more in detail in next slide. Now we have a standard parabolic subgroup, which we denote by P1 minus corresponding to the negative PN pair of associated with Kac-Moody group. And it plays the role of gamma from the previous slide. So we will denote it with the same notation. In 2016, we have studied this group acting on tree, and we proved that the graph of group for this action consists of single array, and we define congruent subgroups of P minus 1 in that group, in that work. Sorry. So in this seminar, we are going to define Eisenstein series for the pair G gamma, and this Eisenstein series is induced by a character on the set of vertices of tree associated with G. This Eisenstein series will be an analog of Eisenstein series, which was defined for PGL2KT by Nagoshi, and the classical non-holomorphic Eisenstein series for the modular group on the upper half plane. We will discuss its constant term, its convergence, and the meromorphic continuation. Any questions so far? Or you can interrupt me at any time. All right. I'm sorry. Let me know if I'm too fast.
Sorry, Abid, I'm a little bit slow. Just now I think maybe I understand. So the point is that PGL2 is the group of adjoint type, and SL2 is the group of simply connected type.
Yeah.
So what you're discussing is the adjoint situation. And is it because there is, because you kill off some torsion?
Mm-hmm.
Is that why you're doing PGL2 rather than SL2?
No,
of
no,
course, you can do the whole thing with SL2.
No, that's it's just a rough analogy. We're not going to use the adjoint group today. We're going to use the simply connected group.
Oh, so then where you say PGL2, it should be really SL2 of KT and so on. I mean, I just don't know why you're talking about PGL2. I was just
he's talking about PGL2 because of the precedence by Efrat and Nagoshi in the 1990s. So they did Eisenstein series on the adjoint group.
On the adjoint group.
Yeah.
Okay, fine.
We're going to use
but that's not a restriction. I mean, you can do it for for any algebraic group or Kac-Moody group. Okay, fine. I think
I'm not sure what would happen if we did it with the adjoint group here, because it doesn't have a highest weight. But I have to think if we use the highest weight in the construction. Anyway, let's just go on from there.
Yeah, sure.
All right. So Kac-Moody group can be classified into affine and indefinite types. So let me briefly survey the results done in these two cases. So Garland introduced Eisenstein series on affine Kac-Moody group back in 1999, and then he wrote a series of papers from 1999 to 2011 alone, and with his collaborator on the different aspect of Eisenstein series. So and then there are some papers by which are of interest here, and let me write. So written by BFK, Braverman, Finkelberg, and Khajdan, and BJKP, where they define Eisenstein series for affine Kac-Moody group over local field, and they studied the constant term. And beside this work, there is a work by Dongwen Liu and Kyuhan Lee and Lombardo. So there is a long list. So if I spend time on describing those work, I think that will eat up the whole time of this seminar. So let me move to the indefinite case, and in particular, hyperbolic case, where the first example of Eisenstein series in this setting came from the work of Carbone, Lee, and Liu in 2017. And there are two submitted papers by Carbone, Garland, Lee, Liu, and Miller over the field of real numbers, and paper by Carbone, Lee, and Liu. Our work is locally compact analog, since we are working on finite fields. So tree is locally finite, and so we get Harmeyer, and this allows us to carry out integration on Kac-Moody groups. All right, so before I move to my technical results, let me introduce some notations. Kac-Moody theory starts with a rank 2 symmetric generalized start with generalized Cartan matrix, and in our case, it's of rank 2, and it is an integral matrix whose diagonal entries are equal to 2 and off diagonal entries are less than equal to -2. And we have two cases. If M is equal to -2, then A is of affine type, and if M is less than or equal to -3, then A will be of hyperbolic type. So associated with G, we have a Kac-Moody algebra, which we denote by this little g. Kac-Moody algebra has a presentation given in terms of Chevalier generators and a billion vector space over Q, and this is called Cartan subalgebra. This becomes a Lie algebra, and it is known as Cartan subalgebra. And then we have pi check and pi set of simple co-roots and simple roots, which are linearly independent subset inside the Cartan subalgebra H and its dual space. We denote by Q and Q check the root and co-root lattices respectively. And we denote the set of root is denoted by delta, and we have delta plus and delta minus, which are set of positive and negative roots respectively. Let W be the Weil group, and we have a set of real roots which are obtained by the action of W on the set of simple roots, and this is an analog of finite dimension root system inside Kac-Moody root system. And for later purpose, we need two subsets of the while group, which consist of even length elements, corresponding to their exponent coming from set of integers and set of non-negative integers. Any question about notation? So associated with Kac-Moody algebra G, we have an incomplete rank 2 Kac-Moody groups, which was constructed by Carbone and Garland back in 2003. And this has a finite presentation given as a set of generators, which are indexed by 1 and 2, and corresponding to the simple roots. And these are automorphism of the K form of highest weight representation corresponding to highest weight lambda. So because Chevalier generators, they act locally nilpotently on the integrable highest weight representation. So this side of these symbols, they make sense. Right hand side, these symbols make sense. So from now on, we will drop this little k and lambda from the notation of incomplete Kac-Moody group, and we will just use G sub 0 to denote rank 2 incomplete Kac-Moody group. So let me introduce few subgroups which we will use later. So we start with certain elements for I is equal to 1, 2, and T invertible element in the field. We define this W tilde I T, the product of these symbols or generators of the Kac-Moody group. Now we set W tilde I to be the value of this element at 1, and these W tilde I, they generate a subgroup which we denote by W delta, and it is called extended while group, and it is homomorphic image of the while group I mentioned in earlier slide. And then we define this element H alpha T as a product of W tilde I and T and Wi, and T is coming from the invertible elements. So let H denote the Cartan subgroup generated by these symbols, HIT for I is equal to 1, 2. Here HIT means H alpha IT.
Abid,
Yeah.
Is it possible to share your slides somehow? Because I would like to scroll back and I don't want to interrupt you.
Sure. I sent it to YC. I already have emailed it.
You have emailed it to
YC.
Yuji, can you? Maybe you could email it to me? That would be so nice. I want to understand, and
I'm sorry if I'm too fast.
No, you're not fast. I'm just slow. So. Or maybe just put a link on your page if it's easy enough.
So Abid, do you mind if I put this in the web page of seminar?
Sure.
If it is okay, I will put that then.
That would be so nice. That would be just so nice. Yeah. Right. It will enhance the experience a lot. But don't let me stop you, Abid.
Okay. So we define for each. Now we know that set of real roots are obtained by the action of while group on the set of simple roots. So each simple root can be written like this. So if alpha belongs to this delta real, then alpha can be written as W alpha I for I is equal to 1, 2. And we define these generators corresponding to real roots, which are obtained by the action of
Actually,
so,
Abid, you were correct when you wrote the tilde on top, because you're in the group and the Weil group's not a subgroup of the Kac-Moody group.
Yeah.
So the tilde is correct.
Yeah. And we denote by use of alpha one parameter subgroup corresponding to the real root alpha, which is generated by these symbols, which I wrote just above it. And G, the incomplete rank 2 Kac-Moody group has a pair of unipotent subgroups, which are generated by these symbols corresponding to positive and negative real roots. And negative real roots are defined as intersection of real roots with these positive and negative roots. These subgroups, U sub 0 plus and U sub 0 minus, these are analog of upper and lower triangular matrices, groups of upper and lower triangular matrices. Any question about these notation?
Actually, they're not just analogs. If you take, if you look at the representation of U0 plus and U0 minus, they actually correspond in ORT of the highest weight module to infinite upper and lower triangular matrices.
Yeah, by fixing coherently ordered bases. I take it. Right. All right, so some more notations. Now we will write G to be representation theoretic completion of G0, which was given by Kac-Moody and Garland. And this group has pair of minimal parabolic subgroup, which is product of H and U plus minus, where U plus is the completion of U plus sub 0, and U minus is opposite to subgroup. And G admits twin BN pair G plus minus BN, which use the Brouillard decomposition as decomposition of Brouillard cells.
Okay, so I understand the confusion. Could you just go back a little bit, a couple of pages back to Carbon, Garland, Kac-Moody groups? Yes. So who is little t? Is it the same as it always was, or it's some new thing?
So there's a typo there. The capital K should be a little k.
Yeah, but what's the little t? It's the same as the little k has a distinguished element called t. Is this it?
It's a parameter.
Yeah, but little k was already
finite field. Little k is finite field. Sorry.
Little k is a finite field,
Yeah.
and then you looked at k, capital K. So, I mean, there was k, formal power series in T.
No, that's indeterminate. Here
that's an indeterminate, and this is
not
that indeterminate.
No, these are values of finite field.
No, it's fine. I got really confused, and I said I'm not understanding.
Sorry, that's a scalar.
No,
okay,
in this case,
just
in
a
this case,
parameter, and it's not the indeterminate in this function field.
No.
Okay, fine.
I'm sorry for
no problem.
these notations.
No problem. Okay. Yeah. Okay.
All right. So
yeah. Okay, fine. It's just a parameter.
And we have a pair of positive and negative parabolic subgroups defined as this disjoint union. Right. Text building associated with G is a homogeneous bipartite tree of degree q plus 1. And as we denote by X, its vertices can be labeled as cosets of P1 and P2 in G, and the set of edges can be labeled with the cosets of P in G. Now, here we can see this part of tree, how this labeling is done. All right, so now Iwasawa decomposition is a powerful tool in automorphic forms. Like what's the routine method is to define a character on torus and then extend it to the whole group G by using this Iwasawa decomposition. We use a variant of Iwasawa decomposition to write another decomposition for rank 2 Kac-Moody groups. So, but let me first state Iwasawa decomposition, which was given by Carbone and Garland in 2003 in the same paper. So for this, we define two subgroups of two subsets of set of real roots, which we denote by delta sub I to real, and it consists of these roots which lie along the branches of hyperbola. And then curly usa by be the closure of group generated by the one parameter subgroup corresponding to the roots taken from these two branches. And if K is parabolic subgroup P1 and P2, then Carbone and Garland showed that G admits this Iwasawa decomposition. Now, rather than taking one of these two Iwasawa decomposition, we combine them to get this decomposition of complete rank 2 Kac-Moody group in terms of I1 and I2, where I1 and I2 are defined.
Abid, the Ks are not fixed points of involutions?
In what context?
In this context, so it's the PIs are what? They're parabolic subgroups?
Parabolic subgroup, yeah. Standard parabolic subgroup.
So why are you calling this the Iwasawa decomposition? I mean,
So
usually the Iwasawa is like K for ordinary groups.
Yeah,
it's KAN.
KAU and the K is, yeah, sorry.
Yeah, sorry.
So who is the K is the U?
No.
K are the parabolics, and they should be.
You can call it. I mean, if you call it Iwasawa, it should somehow specialize to the Iwasawa. But I don't see that. It looks more like yeah. I mean, it's like BGP rather than it's PGB rather than KGB.
I
mean, the U is sort of the. I mean, okay. AU is Samborel, is it not?
It's a Borel.
No, it's different because we have negative. We have negative real roots as well. So it's
no, Siddhartha's right. It is a Borel, but it's of a different cheat system. This in this unique case, there's a spherical building, and the U times A is the Borel of that spherical building.
Okay. Okay.
But see here it has a geometric interpretation where the U is actually the stabilizer of the ends of the building.
You mean U1 and U2?
U1 and U2, yeah.
Yeah. Okay. All right. So I mean, there are things floating around, but I'm not sure that they are spherical subgroups. But if they're not fixed points of involutions, you shouldn't call them K.
They actually were realized as fixed points of involutions by Demetz, Gramlich, and Horn.
Oh, the parabolics were realized as fixed points.
Yes, they were.
Oh, okay. Then.
So this is a geometric interpretation of the Iwasawa decomposition. They wrote theirs in terms of fixed points of involution.
Okay.
But this is geometric in terms of the action on the tree.
Mm-hmm. So we decompose G as a disjoint union of I1 and I2, where I1 and I2 are, so it means it is legitimate to call them Iwasawa cells, right? So we are, so we have here, which we are calling Iwasawa cells. So I want to point out this index. We will call this index or this coset Iwasawa cell. With a component. And any other question from this page?
So 3 minus I means not I, right?
Yeah, because
Okay.
I is equal to 1, 2.
Yeah. Okay, fine.
So when I is equal to 1, 3 minus I means 2. Any other question? All right, so if you don't have any question, let's move to the next slide. So we use this decomposition from now on. So in order to define character on building and extend Nogoshi's work, we need to establish two relations, one between the set of vertices of the building and these Iwasawa cells, and the exponent, which I wrote like a component. Okay, so our first result, which we proved, is that every vertex on X means 3 corresponds to a coset in the Iwasawa decomposition of G. Okay. How did we prove it? In order to prove this, we proved one lemma and its corollary, and this is in this result we proved that the unipotent subgroup at the complete and incomplete level, they can be decomposed as these two subgroups, where U top sub 0 is defined by the symbol corresponding to this finite set inside set of real roots. So let me write the elements of S plus W more precisely. So these are positive roots which are flipped to negative when we apply W inverse on them. So, and the cardinality of these sets is equal to the length of this W. And we define this U sub 0 depending on W corresponding to these sets. And our incomplete and complete unipotent group, they decompose into U top 0 and its complement. Any question about these results? All right, so this proposition gives us one correspondence where we establish a relation between the vertices of our building and the Iwasawa cell. So for the next correspondence, we need some more notations. So we start with the vertex of X, then we denote this omega sub V to be the set of vertices adjacent to V, where adjacent means the distance between the two elements is 1. I'm sorry, there's typo, so I should write V here instead of X. So we consider the set of adjacent vertices. Now this omega sub V can be written as a union of two sets consisting of one vertex and consisting of Q vertices. And because our tree has degree q plus 1. So it means if we fix a vertex, there are q plus 1 edges emanating from each vertex. So we consider those vertices which are adjacent and which are joined by this vertex through these edges. Okay, so and we form this disjoint decomposition of the vertices which are adjacent to V. And if V, which by our proposition correspond to this Iwasawa cell with this A component and I, and we denote the A component of elements of this omega 1V and omega QV by these two letters, then we have more precise information about these numbers, which we write as a proposition. And we have two cases. If our j is equal to 3 minus I, then we get n minus 1 A component. And if j is equal to I, then our A component would be n. And for the Q vertices, we have different situation. So this proposition can be better understood by looking at this local picture. So this is our first fixed vertex, which corresponds to the Iwasawa cell with A component n. Okay. Now, if our this simple root reflection, index of simple root reflection is different than our standard parabolic subgroup, then there is a different. So we get like A component of Q vertices equal to n plus 1, and A vertex of this A component of single vertex is equal to n. And we have same situation with this. I'm sorry if these labeling is not that clear. I can write them if you want. If someone wants.
Abid, just make a note that we should certainly not use K for those sets, because there are too many Ks floating around.
Yeah, I agree.
Also, capital K had it also, it was a field at some point, wasn't it?
It was a field, so this should be a set.
Letter K is field.
Or capital K, capital K.
Capital K is a parabolic, little K is a field. This should be an S or an X or something.
Yeah. So these are the number, like these are the exponents of A component in the Iwasawa cells. Any question about this proposition?
So sorry, I'm just trying to understand. So the Iwasawa components, as you call them, are they double cosets in the Weil group? Okay, so we defined, Iwasawa cells are those, and the by component. So, for example, if I fix some Iwasawa cell, so no, but what I'm saying are the Iwasawa cells indexed by double cosets in the half. So the Weil group is the free group on two involutions, which you call W1 and W2.
Mm-hmm.
And you were taking sequences which were symmetric. In other words, the same number of W1s and W2s.
Exactly, yeah.
And is that the same as double cosets of W by, probably it's the same as double cosets by, let's say, the finite Weil group, which is just a single involution. And then probably there's a Bruja order and so on, and which is okay. Sorry, I'm just thinking aloud.
No, it's okay.
Abid, could you just go back to the where you defined the Iwasawa cells?
Yeah, sure.
So it is over the Weil group, but the indexing is just the exponent of the Weil group.
So this is A component. I'm calling this exponent as A component.
Да.
Ну, у людей же все время кончаются. Вот уже больше года, как у них кончаются, если драйвер лайсенс, они не могут.
Volodya, you are not muted.
Вперед, а назад.
Maybe he is.
These are here, when we consider these particular cosets, then those are indexed over this curly U1, curly UI, and the elements of even length elements of the while group.
Yeah, yeah. Okay.
All right, so now we have enough machinery to define our character and to find a relation between character and adjacency operator, which generalizes the work of Nagoshi. So we define character. If we pick any element in G, this belongs to one of the Iwasawa cells with a component having exponent ni, then we set this character by this piecewise defined function corresponding to j is equal to I, means we have different index of j than this last simple root reflection. Then we have this value of this character, and if they are the same, then we have this value of this character. Okay. And if we denote this by this curly f over x to be the function defined on the set of vertices, and d be the distance on the set of vertices, then adjacency operator can be defined as it was done in Nagoshi's paper by taking this sum over adjacent vertices, the value of function. And our theorem states that this character is an eigenfunction for the adjacency operator t with an eigenvalue equal to q raised to power 1 minus s plus qs. All right. Any question about this part? The material I presented in last three slides, actually, we use those results to prove that this is an eigenfunction for adjacency operator with this particular. Now let me define Eisenstein series. So again, we are denoting our P1 minus gamma 1 such that this intersect non-trivially with curly UI. And Eisenstein's, we have a pair of Eisenstein series corresponding.
Abid, is the character that you wrote, is that actually a character or something, or are you calling it a character?
It is a character. So this character is defined on the set of vertices.
No, but is it a multiplicative character of some group or something? I mean, is it a
Yeah, because whenever we pick G, it because of Iwasawa decomposition, it belongs to one of the Iwasawa cells. So we are defining it in terms of this.
Is Q the order of the field, or is it some new?
Yeah, Q is the order of field. Yeah.
Thank you.
Sure. We define Eisenstein series, which is induced by this character by taking this sum. So the discrete subgroup. The value of the character on the coset, labeling of cosets of Blue-Hearted history. So about the convergence, this Eisenstein series, we prove that this converges absolutely with this condition on the complex parameter S. Okay. In order to prove this theorem, we used this proposition which states that if for any lattice subgroup gamma, we have like the A component of Iwasawa decomposition. It is bounded below by some integer n here. So constant term of Eisenstein series is defined via this integral of Eisenstein series. And we proved that this Eisenstein series, constant term of Eisenstein series can be written as these sums of characters with particular for I is equal to 1, because we are considering the constant term of Eisenstein series E1 S. For E2 S, we have similar results, so we are just focusing on E1 S here.
So here, Abid, you've chosen I equals 1.
Mm-hmm.
So there is there is a pair of constant terms.
Yeah.
But
What do you mean by pair?
I mean, there's oh no, there was an asymmetry. So you don't have a constant term for E2 comma S, do you? There was some asymmetry. You couldn't define it. You couldn't define it for E2 comma S.
Because our fundamental domain is single, right, for the action of P1 minus. Any question? All right, so, and then the series, the Eisenstein we defined as meromorphic continuous. And to show this, we use Hilbert-Bernstein method. And for this, we define Siegel sets and show that they have finite intersection. And we proved that this leads to certain truncation operator, like taking constant term out from the Eisenstein series, and this lives in the finite graph and hence its compact operator. And then using the compact operator criterion with Bernstein method, we obtained the required continuation. So this compact operator criterion and Bernstein method was used by Paul Gertz later ago, and then he agreed to rewrite his criteria, these two criterion in our setting, so as an appendix in our paper. So there are so many details are missing. So we require these two steps to reach at this point where we can use this compact criterion and Bernstein method. And since we are still waiting for this appendix, so I don't want to talk more about it. So let me conclude my presentation by saying that outside of a finite case, our Eisenstein series is the first example of Kac-Moody group over finite fields. So we already have defined congruent subgroup of gamma P1 minus and constructed their graph of groups and have shown that those congruent subgroups are lattice groups as well. So one future direction of the current work is to extend our construction for these congruent subgroups. Excuse me. And also the definition of our Eisenstein series can be extended to the higher rank case without major change, but we don't know which method we can use for the meromorphic continuation. All right, I think that was too quick, so I finished before my time. Thank you so very much for your attention. Any questions?
Maybe I'll just make a comment that would be useful for Alex and for Walter. So we started having a discussion with Ralph Cole about extending this Iwasawa indexing to higher rank buildings. It's a very delicate question. It's a hard question, and somehow either we got stuck or we just stopped communicating because we were busy. I can't remember. Abid, did you remember if we were going to be able to extend the Iwasawa decomposition of the indexing of the building to higher?
Yeah, he was positive about it, but he wanted to have more discussion on it, and he gives some like higher dimensional Kac-Moody group where this can be done. Right. But as you said, it was long ago, and then we got busy some other projects, so didn't get a chance to discuss it further. But he was optimistic that this shifting of labeling from like Bruhat decomposition to Iwasawa decomposition can be done.
Because
In higher rank case, yes. In higher rank case, so
it seems to be needed for the definition of automorphic forms. But in any case, the meromorphic continuation seems to be very hard for higher rank. And I'm not ready to attempt it.
In rank 2 case, we have Paul Garrett's.
I mean, Paul Garrett's also, he's also done something in higher rank. It was of course, everything becomes much more abstract. And this is very concrete because you can do all these computations based on the tree.
So I have a question, or I guess more of a question. More I guess it's different from a question. It's just some idea based on my experience with Eisenstein series for real groups. So you have a constant term formula. That's nice. But you could ask, what about computing Whittaker coefficient? So in other words, constant term is, just sort of take the trivial character of some nil radical, and it's more, but you can also compute Whittaker coefficients. So I mean, for SL2, it's like understanding all the Fourier coefficients, not just the mode 0 Fourier coefficients. And maybe, often these things have some arithmetic information. So it would be good to try to compute Whittaker coefficients, not just constant terms.
So
do you understand? Do you understand what I'm saying?
Yes.
Good.
So we looked at the Fourier coefficients over the real field in another paper.
No, but just in any case, so you have some automorphic form, and then it has some Fourier expansion.
Yeah.
And then constant term is like what's going on with the zero mode, and you compute all Fourier coefficients.
Mm-hmm.
It becomes interesting. And since your things is so explicit, maybe you will get interesting stuff, not just psi back, but something more interesting. It should be a good thing to compute.
Thanks.
You can just look at this. This is what shows up in the string theory and stuff. These Whittaker coefficients. So that's why Henrik. I don't know if Henrik is here in the audience. I don't see him.
You don't see him today.
Yeah. But anyway,
I forgot to mention. This.
He wrote some book about this.
Kleinschmidt, he wrote a paper.
Yeah, with Axel and Daniel.
Yes.
Okay, but what I'm saying is that you have a new thing, so you want to take something new and do old stuff to it, because old stuff was useful in some context. So it's like I expect that it would be something fruitful to investigate.
I mean, by doing this correspondence of vertices from shifting these labeling of this vertex from the Bruhat decomposition to Iwasawa decomposition, it made somehow our mathematical life easier.
So I'm still not 100% convinced that you should call it
Iwasawa decomposition.
Iwasawa, because it doesn't. It just gives the wrong. It kind of says the wrong thing to me.
Maybe
well, it is
you have P1 and P2. Yeah, but no, not even spherical, I guess. It's I don't know if this is some analog of Iwahori rather than if it's parahoric rather than maximal compact.
In parahoric, we have unipotent on both sides.
You have what?
Unipotent groups on both sides.
No, not on both sides. No, the parahoric is some, it's some, yeah. So I don't know, but Iwasawa is kind of doesn't seem right to me.
So
I don't know what's
are these are these notes on the web page? That
Yeah. So
where on the
in
web
the-
page? It's a big web page.
yeah, it is in the seminar web page.
But you go to his where his talk is listed, and right below that. it says-
Below his talk. Okay, thank you.
Yeah.
I'm curious, but I don't really have time to stay for more discussion. You hit a dependence on a choice of highest weight lambda in your computations, and does that mean that for each lambda there's a different Eisenstein series?
No, it's only so it's a harmless assumption that lambda is regular. It doesn't that much. It doesn't.
No, but Alex is correct. For each lambda, there's a group. I mean, we think that they're all isomorphic, but we can't prove it. Of course, in the affine case, Garland characterized the dependence on lambda by determining a cocycle. And we have nothing like those methods available here. So at the moment, we have one for every, we have a group for every lambda.
And there would be a different
different
series for each group.
Yeah. Yep.
It's like the Tom Lehrer song, there's a delta for every epsilon. No, I'm sorry.
At some point, I thought you had the word twin because you had a twin BN pair, you had B plus and minus.
Yeah.
But you never used a twin building structure, which would require a codistance.
Mm-hmm.
So you made use of distance, but you never used the twin building. And you also use completions of the Kac-Moody group. So I believe Walter has told me that these are alternatives that can't be done at the same time. You either use a completion or you use a twin building.
Exactly right.
You can't do both.
That's exactly right.
Anyway, thank you for an interesting talk, and I will download your notes at some point.
Thank you so very much.
Hope to see. Is this was the last one of the semester? You said.
Let me just mention that there will be a special talk in a few weeks.
In June, in June we still have another talk.
Oh, okay. Well, I'll send you out your notices. And anyway, the speaker has thanked the organizers, and I think we should all do that.
Yeah.
Thanks
Thank you
to all
everyone for attending this seminar. So
yeah.
Okay. So I'll see you all some other time, I hope.
see you.
Great, Alex. See you. Thanks for
Bye-bye.
attending.
See you, Walter. See you, Lisa, everybody. Bye-bye.
Bye. Yeah, so probably we should really mention that the on June 4th, at the same time, we will have another seminar talk.
Yeah, it's nice.